Today we have a guest. This torch maker. Look at its flame and don't blink. Are you able to tell when its animation cycle repeats? Even though we're still looking at a flipbook, this one hides a technological breakthrough that is able to cram in twice the frame you'd have even in the most smart implementation of it, paired with a great way of handling movement and edge cases. So let me introduce you to my man Tristan, who agreed to give us a full breakdown of how he achieved this, while also taking the time to package it up in a nice sample project you can get through the link in the description. He is hands down the best VFX artist I've ended up closely working with throughout my career. So brace yourself, as this is how you're gonna feel after you're done with the video.
Thank you, Andrea, for giving the introduction. So yeah, my name is Tristan and I'm gonna assist Andrea with breaking down this effect. The effect itself can be broken up into multiple parts. First one of which is the flames, second one of which is the overlaying glow mesh, third one of which being the glow on the stick itself, fourth one being the smoke particles, fifth one being the embers, and then lastly we also have a point light that emits the scene. But in this part we will first focus on the flames and the overlaying glow mesh. For that we're first gonna dive into Houdini. So this is my Houdini setup, and let's first focus onto the flames. And as you can tell, I'm importing VDBs from an existing template. Although you can create your own simulation in Houdini, like this example I have here. I dropped down a sphere, I squashed it a little bit, and then I added in a pyro source with its mode set to surface scatter, which basically scatters all these points along the surface. And then I initialized it with the source burn, which essentially just created these two attributes called burn and temperature with default values. Then moving onwards, we can transfer this into a volume. And then here you can also see our two attributes being carried over. And that's it, we can now start simulating with the pyro solver. Well, of course, there's a few settings we want to play with. In the setup tab, the first one being the advection reflection, it's set to single project. Because I found that for fire simulations, and mostly for standalone effects like this fire torch, that using the single project will already introduce you a lot of noise that works well with our type of effect. And it's just something to do with how energy and velocities are being injected into the simulation. In the bound step we do nothing, collision as well, sourcing, well yeah, we just source our two attributes. And then moving onwards to the fields, we do nothing. And then in shape, we do have some disturbance, turbulence, and even shredding, as you can tell. Although I won't go too much in depth over this setup, because as you may tell, the core is glowing too much. And I found that Embergen can get you way nicer results way quicker. Although you can probably still make it work with some noise values. Now let's just dive into my Embergen setup. So here we have my Embergen setup. And we're starting off from an existing template. But I made a few adjustments. First one of which is the sourcing shape. The moment I orbit my camera, you'll notice that the shape is stretched. And the reason why is so that when I put my camera this way, when I render out my flipbook, this illusion will introduce more flames and thus give me nicer results. Then also pay attention to the shape noise and the emission chaos. You could probably try to replicate this logic in Houdini to make it so that the core looks a lot better. Then moving onwards, we can start rendering out to a texture, and then you can define if you want a sequence or a flipbook. But I don't want to go with this approach because I want to loop my simulation. But wait, Tristan, what are you saying? You can loop in Embergen as well? And yes, that's true. If you go to the simulation node, under the simulation tab, under time control, the mode is set to, no looping. But why? Well, I don't just want to loop my simulation, but I also want to make it so that my very last frame is flipped horizontally. So that would allow me to flip my texture horizontally after each full loop, which means I would have less repetition and kinda have the double amount of frames, but not exactly. Okay, cool. Let's check out this node. We export 144 frames. Good. Let's start doing the math. I want horizontally 8 frames and vertically 4. That means we will end up with 32 frames. Then I want to channel pack this into the R, G, B and alpha channel, which means we will get 32 times 4, 128 frames. But wait, there seems to be 16 frames missing. And the main reason why is because I want to use some extra unique frames for the simulation blending, so that the horizontally flipped blending to the first frame is using unique frames to break out the repetition even more. Because why not do that? Because as you can see, the simulation keeps going and going. Why not try to use as much of the uniqueness as we can? Okay, and then the directory is set to our Houdini project, and it directly goes into our import folder, and then we say VDB3. Alright, let's go to the file explorer. And indeed, this folder is empty, but if I go up one level there, you'll see a few more folders for different types of simulations, like the VDB2. And then you can make a few random adjustments and then export it to a different folder to then process this in Houdini. Then the first frame, 70, is basically allowing it to warm up a little bit before we start exporting our 144 frames. And the frame stride is the number of frames per frame we want to export. And the reason why I set it to 2 is because on the simulation node, the time step is set to 60 Hz. So it's quite fast. But it may not appear like it because the GPU is trying to render out all these frames. And depending on your hardware, this can go a lot slower or faster. And yeah, that's it. Now we can start looking into Houdini to make the simulation loop. So here we have our first node. We start off from a file node, and then we browse to our VDB, and then we make sure that we import this as a sequence. And then I copied this parameter, and you're gonna see later on, I want to do some file handling. And that's what I'm doing on this attribute wrangle. And if we observe this entire path, what we want to do is we want to store this VDB2 name. So say you make a new simulation VDB3, we then want to register that VDB3 so that we know this is the new simulation that we are creating. And so we have copied our parameter. So now if we create a new string called name, which is this channel string that we can expose, then we can paste in the relative reference into that parameter and then store this inside vex. And now we can start processing this with a bunch of code. So we first start by using a split with each forward slash, and then we store this as an array. And then I grab the total length of my array, and then I want to subtract by 2, so we start from the end of our array. So we take the second one, and then that's how I store the subfolder into an attribute. And that's what you're seeing here on the geometry spreadsheet. And then I also want to do some file handling for the channels, for the R, G, B, or alpha channel. And we do that based on the current frame that we are at. So you'll see the first 32 frames, we are in the red channel, and then we switch to G, then B, and then lastly, the alpha channel. And yeah, we simply use an if statement to each time check if we go over this 32 frames mark, and then we can change the name. With that in mind, we can use that for later on. But first, we can already start visualizing our VDBs. Then what I did was I computed the ranges for the fire color mapping, which will check what is the minimum and maximum ranges. Then also pay attention to the intensity source range here. These are basically our Kelvin values. But how do we figure this out? Well, if we go back to our Embergen setup, within the shading node, here you can already see it from this histogram. But the histogram here is set to fixed values, exactly the same values from our Houdini. So I basically copied it over. Then regarding the glowing color, if we go back to Embergen, and if you keep searching around this network, you'll find at some point indeed this color gradient. And these are basically the same values, although they may appear a little bit different, but they are the same. And then so I added in these pins and assigned the same color values. And that's how I was able to visualize our Embergen simulation in Houdini. Next, we can start looking into how we can have it so that the first frame is blending with the last frame, but it's just flipped horizontally. And let me first explain you how that works. So imagine this is our entire sequence of 144 frames. Then what we want to do is move our entire simulation by 16 frames so that we can start at frame 16 and then have our entire simulation throughout the duration of 128 remaining frames. And that's quite easy to do. We just have to grab the current frame and offset it by 16. So now frame 0 equals 16. So that is the first thing that we need. The second thing that we need to do is take the current other 16 frames and move them over to the very last end, like so. And then we want to blend it in with the current simulation and slowly blend out into it. So now this means that our last frame is looping seamlessly with our first frame. But then before I blend, I first want to flip it horizontally and then blend, which means that it will loop, but the last frame will just be flipped horizontally. And that is exactly why we need those unique frames. So how can we do the calculation to have the first 16 frames move over to the very end and then blend? Well, we can just take the current frame that we are at and then subtract it by 128 and then just add 16. And to avoid that we get any negative frames, we also clamp it with a max operation and then make sure it doesn't go below 0. So let me show you how that's done in Houdini. So these are our two timeshift nodes. And first we want to offset by 16. So let's go to frame and you'll see that I'm grabbing the current frame and then I'm offsetting it by 16. So now when I bring my time slider to 0, it will say 16. And then as I scrub through, it will move along with it. Then in the second time shift, we then want to again grab our current frame, subtract by 128, and then also add by 16 so that it starts from 0 here somewhere near the end. But then we have that issue that all the values before that are going to be negative, but we don't have those negative frames. So we must clamp it, and that's why we use this max operation here, so that if we have any of these negative values, then just use 0 instead. Otherwise, we can indeed rely on these calculations. So then if I click this, anything before that is 0, and then the moment it starts to kick in, it will go all the way to frame 15. Because frame 0 also counts, so that means we do indeed have 16 frames. Then we use a transform node to flip it on the z-axis by setting the scale here to -1. And then we can start blending these two volumes with the volume mix. Now some of you may be wondering, maybe I can try to use the labs make loop node, but that one only takes in one input. So we have to really go with the manual approach instead. So let me focus on this node. And you'll see we keyed the blend from 0 to 1 during these 16 frames. And then this value will slowly transition from 0 to 1. But you'll notice somewhere in between, there's a lot of glow. And it's something to do with how we blend these values linearly. It is not a good approach. But we can try to work with it. We can try to shift these temperature values as we blend so that we can make it loop. And that's what I'm doing inside this wrangle. So we'll want to apply some calculations to shift our temperature attribute. And for that, we need to grab our current blending value. So we copy that parameter. And then if I can explain you, we have that linear curve, but we then want to remap it so that it goes from 0 to 1 halfway through and then back down to 0. And that's what I'm doing in this channel parameter. So we paste it in the relative reference, we subtract by 0.5, and then we multiply by 2. So now we have this red curve from -1 to 0 to 1. But then if I absolute it, it will go from 1 to 0 to 1. And then if I want minus it, it will go from 0 to 1 to 0. Exactly what we need. And then we store it here as this float strength. And then on top of that, we multiply strength with our Kelvin shift. In this case, we push it by 2000 kelvins. So then we can start sampling this curve that we have here and multiply by our strength and then offset temperature with that value. But a curve is usually within 0 and 1 sampling ranges. So that means we must remap our temperature value by dividing it with our maximum Kelvin value. So if we go back to our pyro bake material, you'll see indeed 3500. So we divide by that value. And then these values now are going to be within 0 and 1 ranges. And then once I sample, I can say which values I do want to push and which ones I want to keep, to be able to have good control on the blending. But the question is, you add to temperature, isn't it supposed to be glowing even more? Well, not really, because if we go back to our pyro bake volume, the hotter values at some point become black. So that means the glow will just disappear. So it's kinda cheating it through, but it works. And that's it really. Now what I do, I just store it. Again, I take that detail string and then I grab the full node path and then I can read from my detail attribute called subfolder, and then like so I can generate the export subfolder. And finally we can start looking into how we can render this thing out. So before that we have to first create a camera, and that's what we have here. Then you can also preview it like so, and let's go to the view tab. And as you can tell, its projection is set to orthographic. And vertically, we have the double amount of resolution of the horizontal resolution. And the main reason why is because we have 8 columns and 4 rows. And so if we want to result in a perfectly square texture, then we need the double amount of resolution on the y-axis. And then, yeah, those are my settings. So now we can start rendering it out. So we go to our out network, and here I have added in a mantra node. Then again, pay attention to our output directory. Again, we use this detail string to read from our file handling node to then grab the subfolder attribute, and then we add a slash. So we go one folder deeper, and then this time we read the channel attribute. Okay, let's try it out. Let's take a look into our time slider and let's scrub through it. And as you can tell, we are switching to the G, B, and lastly, the alpha. So it's automatically setting these values in their corresponding subfolders, which is amazing. Then there's a few more settings, although I won't go too much in depth over it. You can just copy my values or download the project files, rendering, limits, render tab. And then lastly, also the objects. So we only want to render out the flame. And then the candidate lights is any light in the scene that I have. In this case, I just drop down a basic distant light with not too many settings. Then you can start rendering it out. And after that's done, you can import these rendered images into the image comp network. There you go. So now we have our R, G, B, and alpha channels. Let's first focus onto the R. Pay attention to the import string again. I use the detail string to then take the subfolder, but then the channel, I hard-coded it. because there's no need, because we'll have them all separately anyways. Then I drop down a ramp to fade out the left and right edges, as you can see in the composite view, just to avoid visible edges or bleeding towards other frames. Then I increase the saturation just a tiny little bit to lean more towards a desirable result similar to the looks of our Embergen setup. Then I sharpened it a little bit, and then finally I mosaiced it into a sprite sheet for our red channel. So then I can start saving this, because I noticed that the mosaic can act up a little bit if you are not at your start frame, and you can see that for the other channels they are just black. But if I go to their start frame, they will then work. Now let's focus on the red channel. Again, the output directory, I use the subfolder from my file handling notes, and then I store this image with a red channel suffix. Then I copy this parameter, because this time I can simply just re-import it again by pasting in the relative references of that parameter. So now we end up with that same path. And then I grayscaled it with a mono node, and then did that for all other channels. And then I started channel packing all these with a channel copy. So you'll see the G channel is our second input red channel, our blue channel is our third input red channel again. And there's only 3 inputs, so for the alpha channel I needed to create another channel copy. This time we create a new plane alpha, and then again our second input red channel. And then I rescaled my texture to a 2K resolution. And then again we export using our subfolder logic with the file handling subfolder. Wonderful! Now we can start focusing onto our last element, which is the knob mesh. So let's go to the object network and reset our camera. So there we have it. Let's now dive in. First, we start off from our torch mesh, which we imported, and then we want to scale it down to 0.01 to respect the Houdini scaling, and then we want to blast out the stick so that we're left out with only the cloth. But the issue is that there's a hole in the bottom, so I shaped a little sphere, which I then merged together with the cloth. So now our mesh is entirely closed. And then I can convert this into a closed VDB volume to then be able to convert this back into a mesh again. Now I can poly reduce it to a realistic amount and then recalculate all the normals. I can even preview them. Oops, a little bit too hairy. Let me just disable it. But I also need a blurred version of our vertex normals, because I will want to use it for our world position offset to create the flames. But if I would use the vertex normals from our actual mesh, you'll see that it will appear too jagged, and using a blurred version of our vertex normals will result in a smoother world position offset. So again, I do a VDB from polygons, but this time I'm smoothing it out with a VDB smooth, and only then I'm converting it back into a mesh. Then I can recalculate its normals again, but this time I'm storing it to the color attribute, which I can then transfer over to my other mesh, like so. And now you can see these colors existing on here as well. And then I will need to do some remapping on my vertex values, because the RobFBX can only take these on vertex level. So I will want to promote it from point over to vertex. But we need to take one step back, because the vertex colors can only be clamped within 0 and 1 ranges, but our values have negative values. So we'll want to remap it to 0 and 1. And that's what I'm doing here in this attribute wrangle. I take the CD parameter and then I add by 1 and multiply by 0.5. So basically divide by 2. And then I will also want to calculate some alpha values to smoothen out the bottom, because you'll notice here there's a bit of a fade. And yes, because we don't want to reveal emissive values there. So I will use the Y position, so the vertical axis, and you can even see as I play with the offset, it's shifting, and then I can also set the range. But now we're also left with some fully transparent triangles and quads. And so we can also remove them. And that's what I'm doing in this next wrangle. First of all, I run over detail, which means that I only run this script once. And then I store the number of primitives on my current geometry. So from the first input, which is basically 0, this one. Then I loop over all of my primitives. And then for each primitive, I grab all of its associated vertices. And then we'll want to check if all our alpha values are 0. In that case, we can delete our primitive. So by standard, we set that boolean to true, which assumes, yes, we want to remove it. And then we start looping over all our vertices. But say if we don't run through our loop, and it will stay 1, and it means, okay, we can remove these, like so. And then I'm also generating some UVs, but you don't need those, so you can also disable it. Then of course, I have to scale it back up to 100. And then I export. So we can just put it here in our Torchfire folder. Nothing specific with the path. I just call it smTorchfireHalo.fbx. And that's it. Now we can start using these elements to visualize our effect in Unreal Engine. Okay, we've gone a long way. Maybe it's time for a little break. So I want to take that moment to talk about a little project that I'm working on. It's more of a passion project, but it has been turning into something a bit more serious lately because we are trying to nurture our ID. And I want to thank Andrea for giving such an amazing opportunity to just take a little moment. So yeah, thank you and definitely go check it out. Alrighty, so now we have reached the second chapter of this tutorial. And now we can take this exported texture and the exported mesh and bring that over into Unreal Engine and start processing these and bringing it together into our effects. And here we have our first emitter for the flames. And as you can tell, it contains a ribbon renderer. Now, if I were to go to the material, you'll see that we're using our texture. And if I browse to it, here we imported it, but we also imported the classical approach for comparison, but also for optimization purposes, because maybe you'll want to use the cheaper approach for lower end devices or for low scalability settings. Now let me just open up this texture instead. What I did, because it contains an alpha channel, I had to set its compression settings to vector displacement. You could also try HDR, but that will only increase the resource size. So the best setting you can go with is the vector displacement. So let's save this one and proceed. Then let's go to our material. And then in here we can use an existing sub-UV function, which is standard contained in the engine templates. But because I want to flip my texture horizontally after each full loop, I will want to create my own function. So what I did was I went in this function and copied all its nodes. And then I went in my own function, this one, and then I pasted it over. But as you can tell, I cleaned it up a lot. But it still uses very similar inputs, like the UVs. In this case, I wiggled the X and Y coordinates because we are using a ribbon renderer. So that's why the flames are pointing to the left. And then we also have our slip images, as well as our time value. And we're also accumulating time with some extra additional value for when we're traveling faster. We want the flames to go faster, but I'll get into that later on. So let's just go into our function first. So we have a whole bunch of nodes, but let's focus on the first comment box, the global values. Our sub images will be the sub images. Then our total frames will be our sub image X multiplied by the Y. So 8 by 4 is a total of 32 frames. Then we'll want to store the global frame info for our two textures that we are going to sample. So that's these two textures, which we then also interpolate with this frame interpolate. So let's go back and let's break this down. If I were to fracture time, maybe if I would also lower the speed to like a multiply of 5, and also exit out of game mode, then go back, you'll see that this one is now always going from 0 to 1, 0 to 1 over and over again, which we then can use as our interpolator. Then if we subtract from our frame, we find our index, which is very similar to a floor node. And I could show you by using a debug scaler and then connect this one like so. It's basically doing the same, but it's cheaper because we're recycling this fracture because the floor itself is doing that fracture again. So we only need to use one fracture. So why not go with this approach? And then we find our first index, which is this index A. And index B is our next frame, so simply add it by 1. And then we take our UV inputs and added in some named reroutes. So for the X, we'll say base UVR, for the Y, base UVG, and then we also have our base UV like that. Just to avoid spaghetti nodes, because we're gonna need these here and there. Now, next we wanna create our UVs. Although normally you wouldn't have to do it. But because we want to flip horizontally, we have that static switch here. So if we want to disable flipping, if false, we will just rely on our base UVs and then use these in our texture samples. Now, if this one is true, what we want to do is we want to flip our texture on the X coordinate horizontally. And that's what we are doing with this one minus. And then we append it back with the G channel to then get our final UVs. The good thing is we only need to figure out this upper row of nodes because for the index B, we are doing the same calculations. So that makes it all simple. Let's just dive right in. First, we grab our total frames, 32, multiply that by 4 because we have 4 channels to scrub through. So now we have 128. Now, if I were to divide that with my index A, so say our index A is at 128, and divide that by 128, it will be 1. So after each whole number, we've gone through a full loop. So then I could floor this to exactly know which loop we are currently in. So we can debug this one. Now you can see this value growing, but it's going a lot slower. And that's because we have set the multiply to 5. But if I were to set this to maybe something like a value of 80, you'll see that this value is now looping a lot faster. But let me set this back to 40. Also remove this one. And then we apply an fmod with 2. So actually, let me bring back the debug. It will all make sense. Now we have a value always toggling between 0 and 1. And that one we can use in our interpolate. So we lerp, either we don't flip horizontally, but if the value is 1, we then flip horizontally, and then we append it back together, and that's how it works. Then we can start sampling our texture, although I won't try to go too much in depth over it because this is quite a common approach. It's also used in many of the Unreal Engine templates. I'll try to give it a go. So we start off by grabbing our sub-images, and then we want to figure out what is our current index on the X coordinate. So we grab the sub-image X, which is basically the value of 8. And then if I apply a modulo operator with our index A and that one, I can actually also debug. You'll see it's this value going from 0 to 7 over and over again. So basically our 8 frames. And then after each 8 frames, we then need to go down vertically. But to know how much we have to shift down, we need to figure out what is the tile width XY. So the tile width XY is basically the resolution of one tile on our UVs. Because indeed our UV is the size of 1. So that means we need to find the size of our tile in ratio to that. And the way to do that is simply by dividing 1 with our sub-image resolution. So I can use the debug flow 2 values. And you can already see, indeed on the X we have 8 and on the Y 4. So that means we need the double amount of resolution on the Y. And that's why it's the double the amount. Good, so that makes sense. Then again, I grab the X resolution. Okay, why? Well, if I multiply my index A with that tile size, then I can floor it to figure out whether we have gone through a full horizontal loop. And then we can also figure out if we should go down on the G channel. I can also debug with a scalar, but it wouldn't make a lot of sense because this value keeps going and it doesn't stay within a unit. But our UVs go beyond that. So imagine there's another UV, it keeps going. So it's fine if that value keeps incrementing. Then I append it back together. And then if I take my UVs, I can take that as an offset, as a lookup index basically. But of course I need to focus on the tile, so I will multiply my UVs with that tile width that I was speaking of. And that's all. Now we sample our textures. We do the same for the index B, and then we can start interpolating. But first we need to pick our channel, because we have R, G, B, and A channels. So similar to what we have done previously for finding whether we have gone through a full texture loop, remember the number 128, but this time we can also do the same, but we divide by 32 because there's only 32 on one channel. So we take our index, and if we divide by 32, whenever the index gets to a whole number like 1, 2, then it means it has gone through a full loop on one channel. And if I floor this, I could even debug this scalar. But this one will just keep incrementing. It only knows when we have gone through a full channel. But if I apply an fmod by 4, now we figure out if we're in 0, 1, 2, or 3 over and over again. So we are kind of repeating the same logic. Although there is this custom node and it may appear scary to you, but it's actually quite simple. There's not much going on inside. We first of all have our result value, which we keep at 0. And then we check if our channel is 0. Then we take the sample texture X value. But if the channel is 1, we take the Y. And else if the channel is 2, then we take the Z. And then otherwise we take the alpha, so the W. And then we lerp with our frame interpolates. And then lastly, we also have a switch for disabling the blending, because maybe you use this on super rapid flipbooks that maybe you don't need the blending anymore and you can save on some costs. And then you could just disable this boolean. And when you disable, it means false. It will just rely on the index A calculations and bypass all the B calculations. Okay, good. Now we can go back to our material. Now, before I go beyond this node, I have to push back a little bit because I'm adding the particle color G with the time value. Because I'm checking whenever the system is traveling faster, then we want the flipbook to go faster as well. So I'll give you a little sneak peek, but I won't go too much in depth over it until later on. But here I have this accumulated forces that I bring into the particle color. So whenever we are moving fast, the module that operates this attribute will detect a velocity change and push it to that and take that as a strength. So this is incrementing, and whenever we stop moving, it stays at that value and holds there. And whenever we start moving again, it will start incrementing again. And that's how I then feed this into the time. Then next I use a quality switch to either say if we want to go with a cheaper method, so in case we're running low settings, or either to use our unique function for the high, medium, and other default settings. On top of that, we also have a feature level switch for lower end devices like mobile phones. In that case, we can also fall back onto our simple method. And then I multiply with a little mask that I created. So I just grab the texture X coordinate and then I remap it a little bit and invert it and multiply just to fade it out again. Again, something you could do in Houdini, but I found it to be okay here within Unreal. Then I store this as a reroute called Play Mask. And then I can use the blackbody to map colors to it. Because we just have grayscale values, we should map some colors to it. So I use low and high temperature lookup values to lure between, and then I can preview the blackbody, and you see now we have way nicer values. Then I multiply with my particle color R channel. I could go back to our system, the R channel, which is being controlled by this flame dim velocity. It's similar to the accumulate forces, but it is detecting whenever we are moving fast, then we want to reduce the glow. And whenever we are coming to a halt, we want to then show more flames again, so we increase the emissiveness. And then I use that as a multiplier. On top of that, I divide the eye adaptation for people who use that in their project. In case you don't, you can just remove it or keep it. Then next I apply a little depth fade for whenever the camera is getting close. I could even preview it. When I get close, it's hard to tell, but it will turn black. Now let me set this subtract to 100, like so. So now at 100 centimeters distance, it will be fully black, you see? And then I can also set a range. Maybe I want to transition instead of within 15 centimeters, 150. So now it will blend a lot slower until we get at 100 centimeters distance. So let me put these values back as they were, clamp, and then I also apply a bit of curving to it, which you can have control over. Then I also want to make it fade whenever it's clipping with other geometry. I use this depth fade. Again, I apply some curving and multiply. Then lastly, I have my opacity for my particle color. So let me go back to my emitter. Here because we don't have a particle state, as you can tell, I removed it from the classical emitters. They have particle states, but because our emitter never dies, yeah, these particles, we only spawn 10 of them and then they need to keep existing. I was able to just remove that particle state, but now we have no fade in value. But I can just take the emitter age and divide it with the duration. In this case, it's just 1. So it means it will go from 0 to 1 in 1 second. And then I will sample a curve. And then we can define how it should fade in. But then I also have a fade out. So I am multiplying this float with another curve that I sample. But this time I'm using the infinite fade time as my index. It's a module that I created. There's a tutorial about it. It is free. You can also grab it from my personal Gumroad. It received a UE5 update. And it's this module. And it's commonly used now among many VFX artists in Unreal Engine. And I also recommend doing so. What this one is doing is it is detecting whenever there's a state change. So say, for example, when code deactivates this effect, whenever it detects that, it will then fade out throughout a specific duration that you can define. Now you can also decide to not use it. And then on your emitter state, you could just set it to kill emitter and particles die immediately. But in my case, I want to have them complete. Let particles finish first, then kill the emitter. So then I use that, a value going from 0 to 1, to sample my curve. But this time I'm fading it out. And that's my opacity. Then I also have some refraction. Now, some of you may already know this, but the base of no refraction is the value of 1, not 0. So that's why I'm lerping with the base of 1. Then whenever we want refraction, we can either decide to go above the number of 1 or below that. In my case, I go to 1.2. But then I also have to multiply with my flame mask. Because if I were not to do that, you'll see refraction on the corners of my sprite. And you'll see, look, there are some weird corners. So when I multiply, now that's cancelling out the refraction. And that's really it about the material. Now I can start really breaking down the Niagara system, mostly about how I create a ribbon positioning. But before I can break down this module, I have to get to the source of it, which is this velocity Bezier curve system module. What it's doing is it's handling the Bezier start and end points as well as the tangent points. And it's done through keeping track of velocity and applying some acceleration and drag to it. We are then also using these values for our color attribute here to define the emissiveness and also to keep track of whether we are moving faster, to make the flipbook go faster as well, and so on. So let's go into this module. First, we grab the velocity, and then I take the length of that and store it as a float called velocity speed, which we will need here and there. First, we want to start by applying acceleration. Our trail end position is the end position above our Bezier curve, and it's local to our source point. So it means whenever the system is moving, that endpoint will always be local to this source point. But then when we detect that we are moving, we take that velocity and we multiply it with our accelerator, which is currently 0.01, and then I subtract that with my trail end position. So now it will start pushing in the opposite direction when we start moving. Then also for the flame dim velocity, I need to apply some acceleration. So that is this value going from 0 to 1, and when we stop moving, it will go back to 0 again. But first we need to apply acceleration. So we take that velocity speed that we calculated, we multiply by our acceleration, and then we keep adding to that value and keep incrementing. And then in the next section, we then start applying our drag. First, we start off by applying drag to our trail end position for our ribbon. We use a custom HLSL node for that. I know it may appear scary, but sometimes I like to use these because it will keep certain calculations very concise and readable. And don't worry, I'll break it down and it will make a lot of sense. So we have a few inputs like our end position, drag, some buoyancy, and the delta. But don't worry yet about buoyancy. We first need to push back our end position towards the source point, so the point 0, 0, 0, because it's always local to our source point. So if we know that, we can simply take our trail end position as a vector to point where we should go to, and then we multiply but zero out the z-axis, because we don't want the z to push back. The z we want to push upwards like heat, and that's why we have the buoyancy for later on. So for now, pushing back, we cancel out the z-axis. Then we take our vector and multiply by drag and delta. But you can imagine if the position is very far away, it will frame by frame travel back, but the smaller this vector is, the slower it will travel back. So it's not going linearly, but that's fine, because I found that when the movement stops, the flames, they should travel back fast, and then until it slows down and eases in a little bit. So in our case, actually, it works really nicely. Then we have our direction backwards and need to apply it. So our add back is basically the trail end position subtracted by our direction backwards. And then we need to make sure that when we subtract, we don't go beyond the 0, so that we clamp these values. So we define our new end value, and then we need to check. So we say, okay, our new end x is equal to, and then we start doing an if statement. So we take our direction backwards on the x-axis, and then we check if it is above 0, then it means originally our value is positive, so we want to stay positive. So that's why we then say, okay, we're supposed to stay positive, but then don't go beyond 0. So we take the max operation, so we don't go lower than that. But then if it's not above 0, it means the value was originally negative. And then, okay, good, but stay negative. So don't go above 0. So that's why we take the min operation. And then we do the same for the y-axis. And for the z, we don't want to do that, but we just add with buoyancy multiplied by delta. So you see, it's not very complicated, right? For the flame dim velocity, we also need to apply drag. It's also quite simple. We subtract the current value with delta time multiplied by our drag, which in this case is 3.3. Then also pay attention to this saturate float. It's a clamp between 0 and 1. Now I could have done this before here, but then when this value goes beyond 1, it would be clamped to 1 again, but then the drag would immediately make it so that this value never gets to 1. So it's always best to let the number exceed here and then apply drag so that the drag can keep it at its highs in case and then clamp after we finish all the calculations. So we're almost done with our trail end position. We just need to make sure that it doesn't exceed a certain range. So that's why we have this Bezier endpoint max range set to 71. So first we need to find the length, but also the direction of our trail end position. Then I grab the minimum value between my max range and that of our current length, and I can then multiply this with our direction, and that's how we can clamp our trail end position. We are also calculating the start position for our ribbon, but in this case it's just a hard-coded value. It may appear strange that I have it set to 8 on the Z, but what I'm doing is that I wanted to have some fixed points. I don't want these to be affected too much by the curvature of our Bezier. So I define this start point here, upwards a little bit, and then what I will do later on in the position ribbon module is I will take a few segments and push them back down again so that these stay fixed and appear a lot nicer with the halo, and it will make a lot of sense later. So for now, just understand that we're pushing up by 8 centimeters. So we're almost near the end now. Now once again we grab the trail end position, not to adjust it, but rather to calculate its tangent. But remember, this trail end position is always local to our source point. So this one not only functions as a point in space, but also can function as a vector. And because it can function as a vector, we can then also quite easily just calculate our tangent. In this case, I take the half of this vector, so I multiply by 0.5. And that then becomes our trail end tangent. And yes, indeed, we will also need a trail start tangent. But that one we can use later on in our position ribbon module, because that can just be our system up axis, which is quite easy to retrieve. So that means we can move on. And then lastly, we also need our accumulated forces. Similar to our flame dim velocity attribute, we then do the same. We take our velocity speed and multiply by our increment, so our acceleration. And then we keep adding to that value we have and store this. On top of that, I also have a static switch that you could ignore, but what I've done is maybe you want to disable this and then it will not accumulate forces and keep this value at 0. But if you want to create controls, then you can keep such switches. That's all. Now we can start diving into our position ribbon module. So now we can start using these system parameters that we have created to then construct our Bezier using the find position on Bezier spline function to then update our particle position. Although it's a little bit more complicated than that. Because, strange, we transform our trail end position from world to local. Wasn't that already relative to our source point? Yes, but only the position, but not the orientation. And if we go back to our emitter here on the properties level, you'll see, funny, it's set to local space. So we calculated our Bezier points in world space local to our source point, and then we transform it into local space. And so now I can feed that into our endpoint, but also I need to take the trail start pause local. Remember, it's a value of 8 on the z-axis. So I add it. So is it really necessary? Not really, but it does make sense to shift these values. For the trail end tangent, we need to do the same. Yeah, we transform from world to local, and then this goes into our end handle. Our start point will just be the start point, and our start handle, like I said, I can use a hard-coded value. Maybe you could go with something more dynamic by checking what is the length of our endpoint and then halvening it maybe. But I found that this works really well because I want to make the source appear more stiff. So using a fixed value worked better for me. In specific, actually, I'm also pushing back a few segments because remember the start pause local is 8 centimeters pushed upwards. And the reason why is so that now I can push back some segments downwards. So I take that normalized execution index from my 10 spawned particles. If you want, you can spawn more, but I found 10 to be more than enough. And then I remap the lows so that we have some negative values. And then I can start doing a check. If some values are going below 0, then we can drift off from that function and instead do some other calculations. And if it's not the case, then yes, indeed, use the Bezier calculations. So yeah, if false, we take our index and then start sampling our Bezier and feed this into here our select. But if true, now it comes, we take our index, which is a negative value, we multiply by a fixed value. We use 25 because it works really well. So now we have a few segments that are being pushed down. But don't forget, we have to add our start pause local, because if we don't, for the first segment that is being pushed down, there will be a bigger gap. So we need to take that also in consideration. So we then add it in and then goes into the select. And that's our position. Now there's some more trickery that I'm doing explicitly for when the camera is facing right above the effects. We then want to avoid that the camera facing will cause flipping. So we start off by grabbing our position, which we then want to rotate based on our camera angle. So we are feeding this into a rotate angle on axis. Remember, we can make this function as a vector and not just as a position, because we always kept it local and relative. So then we need to find our angle, which can be a hard-coded value, but what I do is I sample a curve with our execution index, which means I have a bit more control. Although if I go up one level here on the module, in the end it's just a linear curve. But if you want, you can then start playing with these curve tangents like so. But in the end, I just kept them linear. So you press forward to convert it back to linear. Then I go back. So we have our angle, but we still need to figure out our rotation axis. But the rotation axis is our side vector of our camera. But we can only find it if we first find our direction vector for our camera. So that's why I added in this custom HLSL node. Now, because we are on a GPU emitter, we can then use this custom HLSL to grab the view world view origin. Then I have to convert it from large world coordinates to float 3 values, similar to this convert node basically. And then we return our position. Then I need to calculate the direction vector towards our source point, so the origin point of our system, by just subtracting that vector of our camera with this system point. So now we have that vector, and then I can cancel out the z-axis. So you can imagine, say the camera is pointing upwards. Now I multiply by 0, so now I'm projecting the camera downwards. And then we can normalize it back to a direction vector. Then I can take a cross product with the up vector to find the side vector. So now we have our axis to rotate along. Now make sure to transform that from world to local again. And then we can start rotating. So we have that vector, but I do one last modification. I'm scaling down based on speed. So again, I'm using that flame dim velocity parameter that we have to just multiply down the position. Because remember, the position still functions as a vector, so we can just scale it down nicely. So I'll use this one as a lerp, because this value goes from 0 to 1. 1 means there's a lot of velocity, so we want to shrink down the flames. So I will lerp, and then I'll have a little input here that says 0.8. And if I go up one level, indeed, it's the same value. So now I'm scaling down a little bit here with this multiply. And then this goes into not my particle position, but post position. It's a different way of doing it, but in the ribbon renderer, you could then set an override. It's not super necessary. And that's basically it. That's how this entire setup works. There are some more settings like this set emitter random. It is a random value that I set on emitter level, not on particle level, because then I can here just override the material random with that. So that if you have different instances of your fire torch, then you could have them start on different frames. And then we also have a bit of a scale ribbon width. So whenever there's a lot of speed, we then will also scale down based on our flame dim velocity. Like so. Wow, we've gone a long way. It's really cool to see how we can bring VFX and tech art together. And I'm also hoping that I'm speaking to more than just VFX artists. And I know this one is quite tough to follow along, but don't worry, if there's any questions in the comments, I'll gladly answer them. Besides that, there's also Andrea's Discord. But most of all, I recommend you just grabbing the Gumroad files because they contain all the work that's done in this video in the same format. And so finally we reached the last chapter of this tutorial. Now we're really gonna focus onto the glow of the stick itself. To be honest, I will not have all the time to go over the full effect, but the project files are available on Gumroad. Alright, let's just dive right in. Now, back in our system, we have already covered the full ribbon flame emitter, and then we can focus onto the next one, which is the halo overlaying glow mesh. So we have a mesh renderer, which is this smoothed out version from our not part of the mesh. Remember, we previously exported it from Houdini, so now you can import it here inside Unreal Engine to be able to proceed. One important thing to do when you import the mesh is to set the vertex import to replace. And I'll cover that part a bit more in depth soon. So let's just go back to our system first. And we have this halo overlaying glow mesh material. And as you can tell, we are sampling our flames from a noise simplex node. So that one is indeed a little bit more expensive. However, we needed it because we want to pen those values in 3 directions. And so we have no other choice. And I can show you this by singling out this emitter. Let me go back here. You're gonna see the moment I start moving, the noise values start to pan a bit more rapidly. And also pay attention to the world position offset on our vertices. Whenever we stop moving, these vertices start pushing more upwards together with the noise. And then it will also play along with the direction of my character's velocity. See? So I'll start breaking down now. Our emitter is just a GPU emitter. It could be a CPU as well if you really wish to. Our emitter state is set to loop only once. And we only spawn one single particle. So now you may be wondering, okay, what do we do if we want to kill our particle? Well, remember we have this infinite kill module. I've already covered it previously, But I could repeat it one more time. It's this custom module. I also have a tutorial about it on my personal YouTube channel, and I really recommend you to just grab it for free from my Gumroad. It's really an amazing module. It will really put your VFX to the next level. So I could do another breakdown of it, but what it's really doing is it's detecting a state change, and then once it does, it will start taking a value. In this case, we have it on 2 seconds, and then after 2 seconds, our particle will kill. So if we enable the parameter rights, we can then see the particle alive data instance being set. So it will be set to false whenever the deactivate is detected after 2 seconds. So now code can say, before destroying the effect, just deactivate, and then it allows the particles to do their thing before getting destroyed, which, you know, visually is necessary mostly for such realistic VFX. So that's that. Now we can look into how we can pen these noise offsetting values. We can't do that in the material because we have to accumulate the value, because it can go in any direction based on our velocity. And the velocity I use is basically the trail end position. Remember, we can use it as a vector because that position is local to our source point. This emitter, say on the ribbon flames, is set to local space here as well. So these values are local. However, their orientations are not local. So what I can do is transform that vector from world to local space to also have that vector or position, let's just say, in local space with its orientations. Now I can normalize it to actually find the direction I should start incrementing my value to, which I will then add to my halo flame offset. And that one is a vector 3, and you'll see I keep accumulating and keep setting that value. And I'm also feeding that into my dynamic parameter, my first index. So if I go back to my material, oh yeah, indeed, we are reading it in. We are then adding it as an offset to our world position to then sample our 3D noise. Okay, let's go back. Then we need to use this vector and multiply with our panning speed and also our delta time here. It's a little bit chaotic. Let me just add a little pin to clean it up like so, to then keep incrementing this value. It's really that simple. So this value keeps growing, or it keeps going down wherever you go. You are moving to. All right, let's go to the next one. We have our flame dim velocity. Remember, this value is incrementing to the value of 1 whenever we move fast, and then the moment we stop moving, this value goes slowly back to 0. So that means the value of 1, we're moving rapidly, and the value of 0 means we're moving slowly. And then I use that in a lerp, set the different speed ranges, which I then also multiply with my panning speed. But I'm also using this flame dim velocity to feed it in over to my second dynamic material parameter, because I will also use it in my material. And among that dynamic parameter, I'm also sending over the trail end position, but this time in roll space, because I'm gonna need it to push the world position offset on my vertices in the right direction, which is of course not in local space anymore. So now we can break down this material completely. Actually, if I want to break down this material, it's also better to use the mesh as a preview for the material that we're building. So let's just browse to it and then set the preview to this mesh, like so. Press F to focus onto it, and here we have it. Alright, now the globals. We are first extracting the blurred normals from the vertex colors. So very similar to the vertex normals in world space, these ones, but what we have done in Houdini is we have blurred these and then stored it in our vertex colors. But the issue with vertex colors is it cannot have negative values. So we had to map them from -1 and 1 to 0 and 1 values. And then we can just map it back by using a constant bias scale. So we subtract by 0.5 and then we multiply by 2. But before all that, we have to also make sure that we map it from local to world space. So now we have a very similar result, but indeed smoothed out. And we're gonna use it here in the world position offset. So let's stop previewing this one now and look into the next one. This one is just the center. It sets a center point that we want to eyeball. So somewhere 12 centimeters above. And then indeed, again, we map from local to world space. But in this case, we have to transform the position. And then we store that as our center. Now we can start sampling our texture. We have already gone partly over it, but let's just do so one more time in detail. So we grab the world position, which I then transform from world space into local instance and particle space. Then I add the halo pan flames offset to these coordinates. And then on top of that, I also use the particle random to offset these coordinates, because maybe you want to have different instances of this effect in your scene, and then these will then make sure that the values are not always the same. Then this goes into a quality switch, in this case default, and then we use this vector tree as our coordinates to sample our noise. But if we are on Epic, then what I want to do is I want to modify this noise a tiny little bit more by adding some distortion. And that's why I use another time a vector noise. I use a divide to adjust the frequency a little bit more on the coordinates, and then I sample it, and then I multiply with a low value to then add it to distort my UVs, which will help to just use it for cinematic versions of this effect where you want more distortion in it, although it's not super necessary, so that's why I kept it on Epic. And even for low, you could use the UVs. Remember, in Houdini we generated this projected UVs, and then you could use that approach, or maybe you could use triplanar calculations. So feel free to play around with these inputs, they are available, but they will fall back to the default if you have nothing there. Good, then we have our noise, we can just preview it. Here we have it, and then I invert it, like so. So now we can see more of these black spots in there, which is what we're trying to recreate. Then we can actually start using this noise. First I apply a pow by 4, so we get more of these black values. And then you can also see more of the Voronoi lines coming through. Then here, with this parameter, I add and then multiply, similar to a bias scale. But now I have a bit more control over it, because this is now a parameter. So as you can see, I'm shifting by 0.191, and then I'm also multiplying by minus 0.3. And then I'm using it to shift my Frenel calculation, which is this one here. I grab the vertex normals and the camera vector, and if I then take the dot product with those two, then we get a Frenel. Then I add it, and you're gonna see some of these lines start to break through from the silhouette, but also from the core a little bit. It might be hard to notice, but it's definitely helping a tiny little bit to make that Frenel a bit more alive. Then I will use this to sample a few different curves. Now know that this is a value going from 0 to 1, so now I can actually start playing with it. So let me maybe preview this channel separately, starting with the alpha. You can see now I'm mapping a curve going from 0 to 1 quickly, and then it goes down a little bit. And then I can also show you this curve asset, and you'll see on the alpha, oh yeah, it goes up to 1 and then goes down, but not entirely. And then I'm using a few different types of curves, so I'll show you them already. This one, and then the green one, which is quite similar. And on the red channel, I didn't add anything. So perhaps what you could do is you could maybe move one over, like the alpha, you could bring it to the red channel, but it's not really necessary. Okay, let's go back. Now let me remove this one now. Then I multiply that curve with my alpha Frenel. Now you can see that same noise, but it's breaking out the silhouette a little bit. And yeah, it looks a lot better. Then we can start sampling our blackbody. So here I then lerp between my low and highs, and then I sample my blackbody like so. Then I multiply with an emissive boost, and then I lerp in some blue glowing values. Although it will be hard to read here, but they do kick in, and they are really gonna pop through once I start previewing this multiply. But it's tricky to add it in with the blackbody, so instead I'm lerping them in with another mask that I created here. So let me show you that. I'm using the flame dim velocity to control it. Remember, we sent it over from the Niagara system. This value goes from 0 to 1 the moment we are moving fast, and then the moment we stop, the value goes back down to 0. So whenever it's moving fast, we want less glow and maybe more of these blue glowing values. And I could show you that if I disconnect this and bring the flame dim to 1, you're gonna see more of these blue values coming through. And then 0 means more of these red values and less of these blues. Okay, so let me first reconnect everything. Then I'm remapping this value to then bring it into another lerp that is using that same texture again. So let me preview as an alpha. And this then goes into my lerp, but I'm inverting its colors. As you can tell, now the lows are being mapped to the value of 1 and the highs are being mapped to the value of 0 or minus 0.7. Now I can also show you that. Let's break out of it. And then whenever the flame dim velocity is 0, you'll see more of these black values. And when we set it to 1, you'll see a lot less of these black values. So that means now more blues will be blended in from this lerp. Then we multiply with our Frenel as well to have a bit more control over the looks of it. Let's reconnect everything again and move onwards. Then I multiply that with my Frenel here that I created, but I'm recurving it. So now I'm introducing a bit more of the white values because my exponent is set to 0.8. It's just a tiny little tweak, which I then want to mask out with the bottom of my effect. And remember, in Houdini we created these alpha values on our vertex colors. So I then recurve it and then bring it together with a min operation. It's very similar to a multiply, but sometimes I want to switch it up a little bit, and sometimes it can give you better results depending on what you want to achieve. Then I multiply this and finally divide it with eye adaptation for people who use this in their projects. But if you don't, you can just bypass it. Then there's another control here in the opacity. I use the flame dim velocity, and whenever the system is moving faster, I want it to glow a lot less. And note that this material is set to a blend mode of additive. So we could also just use this in a multiply in our emissive colors, although it wouldn't make too much of a difference. You can also do it this way, basically. Now the fun part, the world position offset. Although before we can start adding the world position offset, we need to figure out an attraction point for where the vertices should push to. And then we should also create a mask so that not all vertices are getting pushed. So first of all, we sent over the trail end position. Remember, if we go back to our system on the halo emitter, halo pen flames, we had sent over the trail end position into our second dynamic parameter, so 1, along with the flame dim velocity attribute, this one. Let's go back to our material, and as we click on this parameter here, indeed it's set to 1, correct. I then append these to then finally normalize it as a normalized direction. Then I multiply that with a strength. You can imagine now a point that is being set a distance away along that direction to create some space to balance all these values. because I'll also have to add in some predefined vertical offset value that is actually in relative space. So I'll have to transform it from local to world space. So now you can imagine I have a value that is always right above the knob mesh that is always following the orientation, because I figured out that the ribbon flames, no matter where the trail end position is, we still had to tweak the vertex offset on our halo, and that's why we have that predefined offset. But because the ribbon is so dynamic, I needed to add in two of them, because if I go back to the system, back to the ribbon flames emitter, in the position ribbon, remember we scale down our ribbon depending on how fast we are moving. And because of when it's getting scaled down, I also had to readjust these local offset values to make sure that the world position aligns nicely, and that's why I have two of them. Alright, then all I have to do is add this to my center point, which is basically this global value here that I created, which you can use for other purposes as well. But in our case, we use it once. Then we find our attraction point. Then we can take the vector from that towards our vertex world position to then find the vector that we can normalize. And then if we take the dot product with that one, we can then create a mask. And then we can remap it so that we can control the lows and the highs, so we can have more black values. You'll see when I preview, I have this mask. And this mask will always orient itself towards this trail end position, along of course with these values that we added on top. Then I multiply this with my vector. It's hard to tell, but this is actually a vector, which is masked out. And then also I want to multiply this with my noise, like so. Then I multiply that with my world position offset strength. And lastly, I then multiply this with my alpha vertex color mask that we created in Houdini. And then to control the curveness, I use a power by 2, but you could also just multiply the alpha with the alpha, like so. This would be cheaper, there would be less instructions involved, but it's fine for now. At least we have the control if you want to. And then this goes into the final multiply directly into the world position offset. And that's all. And this is where I will bring this tutorial to an end. There's a whole lot more bunch of things to cover, like this glow on the mesh itself, or some other things like the positioning of these smoke particles, and the way that they slowly detach from the source, and so on and so on. Also the sparks, but you know, these are little details. Here as well, this is a light function that I use for the light source that also exists in the blueprint. The blueprint itself also has some similar logic for the acceleration and the drag, because the point light and the mesh don't exist in the Niagara system. Or if you still have some questions, you can always ask me or get the files from Andreas Gumroad.
So for those of you who made it to the end, this was a bit of an experiment, a different kind of video from my usual ones. If you enjoyed it, and if you have any other ideas about what we might bring here next, let us know either in the comments or in my Discord server. Either way, I'll catch you next time.